Hi and welcome to a new video in this series. Today we're going to see how procedures in Fortran are declared. They always go inside a contains statement, and it has to go at the end of the program or in a module, which we will see in later videos. We have two types of procedures, mainly functions and subroutines. In order to declare them, we have to use function, for instance, and then as we're in Fortran, end function, and the same for subroutine, so end subroutine. The spirit of a function is to hand in some arguments and get a single result at the end. And the spirit of a subroutine is to hand in some arguments, perform an action, and not necessarily have a result at the end, rather say modifying the arguments that you handed in or some arguments that you want to get out of there. Now let's name this function, say square. In order to get the square of the value x, and here square as well for good practice. And for the subroutine, let's call a normalize subroutine. In order to normalize, say, a vector x, it doesn't matter that the vector or scalar x has been used in different functions or procedures. These are dummy variables, so the name we are assigning here have a local scope. That is to say, if we are using x in this subroutine, it is different from the x in this function. So this x here only can get used up to this part here in the function, and this other x here can only be used inside the subroutine. So normalize, and let's declare the variable x, so real, and let's make it the default for the moment, x, and in the function as well, real x. Here is where the differences between functions and subroutines start. For the function, we also have to declare the resulting value. In this case, we can use square, real square. So the square, that is the name of the function, is used as a variable itself. So here we're specifying that it is a function from R to R, so from reals to reals, and square is the resulting, the result, and it has that variable name. There is another way of doing this. Instead of doing it this way, go here and use the result sentence in order to declare another variable. So instead of using square as the name for the return variable, we're going to be using y. And you also have to specify, as in everything in Fortran, the type of the variable y. In this case, it's going to be real, so it is still a real-to-real function. Here in the normalize, however, we don't need to declare any return type. We just have to perform an operation here. Say, for instance, let's declare a local variable, so real, say n, where n is going to be the normalization. So n is equal to x times x, and then x is equal to x divided by n. So we are normalizing x, assuming that x is a vector. In this case, it's a real, so let's say dimension, and let's have a deferred dimension. What does it mean? The column here indicates that we're going to be working with an array that has dimension 1. It will be starting from the default 1 in Fortran, and it goes up to some dimension, some number, which we don't know yet, but it is well defined. That is to say, we're handing into the subroutine a vector that has already an allocated dimension. Going back to the function, we're going to then return the x times x as the variable y. We do not need to specify, say, a result or return in these functions or in these subroutines, as in other languages like JavaScript or Python. You do have in Fortran the return clause, but it is not used at the end because it is implicit in the end function that we will be returning the command to where we got called from. Now let's check out the intent. It is an attribute that each variable will have, and we'll use it, say, here intent, like that. We have here a variable which is intent in. That is to say, it goes into the subroutine. It can also go here into the function, so intent in as well. And in both cases, it functions in the same way. We're telling the compiler that we're going to hand in x as an argument into the function or the subroutine, and we cannot modify it, or we will not be modifying it in the function or subroutine respectively. If we try to do it, say here x equals x plus 1, the compiler will throw an error. In the same way, there's an intent in, there is also an intent out. For that, we also need another variable, so let's call it, say, y, and let's add it here in the same way. So say y, and the intent here then would be out. This variable basically tells the compiler that we're going to be handing in a variable y, and its whole purpose is to be returned to the main program with a change or a new or perhaps a created value. So if we are using y here in the subroutine, for instance, we should assume that y has no relevant information inside of it. If it were to have some relevant information we want to use, we will then use in out. That is to say, it is an argument which we'll be using for intent in. We will be using it in the subroutine with the value that it had before, and intent out as well, so we can modify it in the subroutine, and its intent is also to be modified there and go out as well. So those are for the different types of intents that are in each kind of procedure. For the function, the intent in attribute for all the arguments we're handing into the function is kind of the spirit of function, and a single resulting value, in this case y, it is also in the spirit. That is to say, we perform no input-output operations or anything of the sort. We do not modify the variables we're handing in. It is very much in the spirit of mathematics, and it is in the heart of Fortran. There is actually a way to specify that, which we will be seeing in the next video. And for these subroutines, we have intent in, intent out, and intent in out. And it is a way of organizing all your code. If you are having, say, actually, let's remove this one. Now, you should always try to construct this subroutines and functions in Fortran and specify the intent of all the variables which you are handing in. For instance, here I lazily called it intent in to showcase an example, but it's actually an intent in out. We can see here we are using x, the original value of x, and then we're modifying the value of x. So for precision, it is intent in out. If you're using a dummy variable, so for instance here n, which is used only locally inside the subroutine and nowhere else, then you do not specify the intent because it is not a part of the arguments you're handing in to the subroutine or the function. If we were to call the subroutine then, and here we go into how to call the functions and subroutine. For the subroutine, we say call, in this case normalize, and we hand in the argument. So let's say vector. And let's also declare this a real, and say, let's call it like this, vector 5. So here, let's give it some values, 1, 2, 3, 4, 5. These are all integers. They will be implicitly converted to the real default precision here. We hand in the vector vec to the normalized subroutine. For subroutines, we use call. So as you can see, the argument we're handing in is not necessarily named the same as in the subroutine, which is very useful. You can organize your code better that way. For functions, you do something else. So let's actually go back here and declare, say, m, and let's give it a value of 5.5. So a declaration of m is equal to that, and we're actually going to need another variable. So let's say m square. We do not initialize it. There's no need. And so m square is equal to the function, so square m. As you can see, the functions are used precisely as in mathematics. They are always in the right-hand side when you are using them, and when you're declaring them, like here, they are in the left-hand side. Once again, you don't need to use the same name. In this case, we used y. We could have also used the other way of naming things. So instead of result, we use the square name here. And in this case, then m underscore square is equal to the function square evaluated at the value of m. Now that we have seen how to call these functions, how to define the subroutines and the procedures, let's talk a little bit about scope. These variables, vec, m, and square, are global variables, so we can use them throughout the entire program, included in the contains section. So we can actually use, say here, x times m, and this would be very well defined, even though we have not declared m inside the function. That is to say, since we have a program which has variables vec and m, for instance, and we also have the definition of the functions and the subroutines, those functions and subroutines have access to the variables declared outside of them. However, the program itself does not have access to the variables declared locally. So if we try to use y here, somehow, that would be a compilation error. This is very useful when you have, say, similar functions, or you want to produce a whole package and use the same variables x and y for different functions. You can simply use them and there is no conflict at all. They are defined locally. And the variables which you will have to be careful with are the global definition of the variables. This ties in nicely with the next attribute, which we will be saying now. It is, say, optional. So let's call it n. And let's declare n as integer. And let's see the optional. As its name entails, it is an optional argument, so we can or cannot include it as an argument of a function. So here we say if, and in order to check if n is present and avoid compilation errors or runtime errors, we say if present n. So this present function, which is intrinsic to Fortran, checks if n is present as an argument of the square function when we call it. So if present, say x, let's do something simple, x equals x times n. So we multiply x by n just to do something with it, and then do this. So we're going to be using this new definition if n is handed in with x as well. Because this is an optional argument, it is very important to see how these arguments are handed in. So when calling this new function square here, suppose we have another integer then, and let's call it L equals 5. Here we cannot actually use this. So this would be wrong because the first argument of the square function is a real. And the second argument, which here is real, is supposed to be an optional integer. So if we're going to hand in the arguments, they must be in the same order. So here, L. This would be correct because M does have a real type and L does have an integer type. If we want to actually hand in a third value, so let's say H, and let's here call K. So N and K are both optional. We also define it here. We must be careful with the ordering of these two values. So let's say here H equals 3, so it's defined. If we want to use the first argument as 5 and the second argument as 3, this is correct, but we cannot change the order because now N in the function will be taken as 3 and K will be taken as 5. In order to avoid this, Fortran has the specifications of the original function argument names, so N equals and K equals. In this case, you now have the possibility of changing the orders. So we wanted H to be K and L to be N. So we call the specific optional arguments by name to make sure that we're handing in the correct argument. This is particularly useful in the case, say, we want to specify k but not n in the subroutine, so we would say k equals L, or h in this case. The first argument we're handing in to the function then is m. It is mandatory and it is real, just as in the function. However, we're skipping the second argument entirely and going to the third, and that is the second optional argument, by specifying the name of said optional argument. This is very useful, and it is part of many Fortran intrinsic procedures. We're going to be using it in the future when we write to files and from files to specify where to insert new data, how to read the status of the file, if it's the end of file, if there's a file corruption, and everything else. The last thing we have to mention is there's a save attribute, which is the default when you specify the value of a variable at the beginning of a function or subroutine. That is to say, if you call a function twice, this initialization will be saved. So the next time we call the function square, this n will have the saved value. So if we say here n equals 5, modified there, it will be saved as n equals 5. So let's make a counting function, say function count. We're not going to hand in any arguments, and function count. I'm going to be using the other way of specifying the name of the result, so say count, that is with the same name as the function. And let's give it a n, an integer, I mean. Save n. And here count is equal to n, and we increment n equals n plus 1. So we are incrementing the value of n, and here count returns the result n. This attribute can be initialized to 0, and so every time we call the function, the count is incremented by 1. Notice, however, that even though we initialize the n value at the beginning of the function, we will not be reinitializing the value n. We will have n equals n plus 1, so the previous one plus 1. It only initializes n equals to 0, it only sets it to 0 the first time we call it. It has to be used with care, especially nowadays with parallel programming, in order to avoid conflicts. However, it does have its use cases. For instance, for random number generators, very easy to program random number generators can use a save variable to use the previous random number to generate the new random number, and in order to generate pseudo random numbers, which are of a lot of practical use in physics. Finally, I will mention that this save attribute here is redundant, as I said, by default when you are declaring a variable here, and this is something implicit you should know about Fortran. If you're declaring the variable value here at the beginning, it will be by default a save kind of variable. But for clarity, including the save attribute here is good practice, so you should try to do that. Now let's see if the program even works. So let's write and quit, and let's say Fortran procedures incompatible rank assignment, right. So I forgot that in this part here, we used here. We changed the dimensionality of x, so x is defined as a deferred type, but an array. In this case, x times x will be made, will calculate this element-wise. However, n is a real and it is a scalar. So here I wanted to use the sum intrinsic function, which we've gone over in the last video, and this will return a single scalar. So this should now compile. Write and quit, and yes, it does compile. Generates a.out by default, and let's run this a.out. We did not print anything. Let me fix that. All right, so I have defined the integer I to do a loop over the count. So each time we will be printing the count. Given that the count is a function and it will return a value, we can set it up in this way. So we print the count. So we print the call of the function. That is to say, we print the result of the count at that I. And this should count from 1 to 10. For the square, we simply print square here. X is equal to the value, and x squared is equal to the value squared. And for the normalization, we print the vector before and after the normalization. And let's try that. So gfortran, and let's see the result. As you can see, the original vector, 1, 2, 3, 4, 5, and the normalized vector, the x is 5.5, and the x squared is a bit more than 30, that's correct, and the count goes from 1 to 10. So that's it for this video. I hope you enjoyed it. If you have any comments, do leave them in the comment section below. And next time I'm going to be going over the specifications that these procedures can have, for instance, the elemental or the recursive attributes.